environment and the genetics?
Well, a theme about this Apimondia is that beekeepers are farmers, and as we all know, farmers have a love-hate relationship with the weather, and beekeepers are no exception. This is a small part of a large project in Canada called the Biomics Project, in which we've been looking for genetic markers that we could use to breed better bees. In the course of that, we had to deal with quite a few different conditions. So the plan for the project was in 2016, collect hive performance, how much honey, survival, colony size, etc., from 1,000 colonies spread all over Canada. In 2017, we repeated it, but with only 500 colonies. And since then, we've been sequencing the bees that we collected and doing what's called a genome-wide association study to see if we could find genetic markers that say, okay, these should be better honey producers, or genetic markers to say these should have better winter survival. I'm not going to go into the genetic markers we found because there's a good talk this afternoon by Emma Zayed, and we have a number of posters up on that. But I'm going to talk to you about filtering through some of the noise that the environment provides. Now, we do have bees that we know are better at certain traits in this. People from the University of Alberta and the University of Laval and even some government programs have been selecting for 3 to 6 years for better hygiene in their honeybees. And they've upped the hygienic rate, the rate of clearance of dead bee larvae themselves, to an 80–95% hygiene rate over the course of that selection. So they've been selecting strongly, and we know that there's strong heritable components to that. So we should be able to see that in our data. So we kind of salted in bees that we knew we were going to be able to find some kind of genetic result from. But stuff happens. So the first year of our study is the only year I'm going to talk about. We had lots of colonies in Ontario, and we had one of our worst droughts and heat waves ever. And that, we've talked about climate change, it really is happening, and it strongly affects beekeepers as well as the forage that the bees find. This wasn't just a problem in Ontario or the prairie provinces, where beekeepers get some of the world's highest honey yields. We had the warmest spring on record, some of the highest temperatures ever recorded. And those colonies achieve a lot of their honey production from the canola or rapeseed crop, which is a crop that is well adapted to slightly cooler temperatures. It's not really a tropical crop, but we have big heat waves. So the weather was a strong factor, and then we had a lovely set of colonies run by the people at the University of Manitoba, and about half of those colonies were knocked on the ground by a series of tornadoes that whipped through our yards. And so you can see we had just a few exceptional weather events to account for and try and filter out when we were looking at our data. So what we did first was to ask, how does weather affect all these honeybee traits? And this has been studied for a long time, and there's actually really good old data. This is from the beginning of the paper where somebody kept 29 years worth of data in Iowa. And because weather is so variable from year to year, these long time series are really helpful at getting a handle on what's going on. Recently, somebody used a long time series and plotted actual versus predicted from the equation that used weather variables. And you can see it's a pretty good fit. So any of you who are really interested, that paper by Holmes from 2002, striking how much weather does control honey yield. So for many of you who are beekeepers, I know this is not a big surprise, but this is one of the things that we had to deal with. What if some parts of our genetic project is actually getting a much bigger signal from the weather than from the genetics of the bees? So that's what we had to filter out. Rather recent paper did a nice job with monitoring from second to second, essentially, what the temperature and sunshine around the colony was. And they also had monitors at the entrance and exit from the hive to say how many workers were going out to forage. So the workers going out are the blue line, and the gold bars is the sunshine, and the red is the temperature. And you can see that in this partly cloudy day, during moments when the sun was out for longer, more foragers went out, but by mid-afternoon it wasn't as strongly correlated. So that tells us it's not just temperature, although temperature is certainly a big part of this. I mean, if it's too cold, bees can't fly, but the sunlight conditions and also the humidity all have an effect. Now, as it happens, these days, our excellent satellite and other national and international weather agencies collect some of this very detailed data for us. So this is a plot I made from data I downloaded from the NASA National Oceanic and NOAA database. And this shows the average daily temperature during the day, because we're not really worried about what's happening at night, in one particular location where we had yards. And you can see the big fluctuations. If you can see the dotted blue line, that's approximately where bees begin to fly. And you can all come and tell me later that your bees fly at a higher or lower temperature. It's about 12 to 13 centigrade. And perhaps if your bees are well cold adapted, they might fly a little bit sooner. But below that line, there's not much foraging going on. The dotted green line up around 19 degrees is, well, above that, it doesn't make much of a difference anymore. They're out anyway. So there's a sensitivity zone in there. And you can see the portions of May and June, the weather was moving in that sensitive zone, so it makes a difference. And so what I did, I put together lots of different weather variables from the satellite data in the 56 different locations around the country where we had yards. And the variable that turned out to do one of the best jobs was what you can think of as the number of degree days, where degree days is measured as a number of degrees above 13 centigrade. And so that's what I will be talking about. And just to point out that these variables were very different between our 2 years. The dark bars 2016, the gray bars 2017. You can see 2016 was a lot hotter than 2017 in most of our locations. All right, so I'm not going to burden you with lots of data slides. I'm going to tell you some wonderful stories about lies, dandelions, and statistics. The great news was that combining temperature and sunlight data explains 73% of the variation between our colonies in one of the measures that we did. So one of the measures we did is we tried to weigh them at the beginning of a nectar flow and 2 weeks later. So we tried to catch how much weight they could put on during a period when it should have been growing. So when we weighed them varied because different parts of the country have the nectar flow at different times. So we measured that 2-week weight gain. And of course, some colonies had already gotten bigger at the beginning of it, some were smaller. So I actually used the ratio of the final weight to the beginning weight because that told me how much proportionally, what percentage gain did they get during the nectar flow. And I used weather from 3 weeks, the week just before the measurement, the first week of our measurement period, and the second week of our measurement period. And it's amazing how much of the variation in that 2-week weight gain those weather variables accounted for. So remember that this is 56 locations, although several of them are clustered together, so it's probably about 50 locations in terms of the weather data. So when we look in at the more detailed data, it really differed depending on whether you're looking at eastern Canada or western Canada. But remember some of those first slides I showed you, we were getting different exceptional weather conditions in the west and in the east. And one of the three weather variables, the one in the middle, the first week of our measurement period, the warmer it was, the more the colonies gained. Surprise, surprise. Because most of our nectar flows were timed at June, and June's not that hot in most of Canada. The week before, I had a negative relationship between temperature and weight gain. Why? Well, if it was warmer the week before, their starting weight would be higher, and we're dividing by that starting weight. So, you know, we were trying to say just what's happening during this 2-week period. Oddly, the second week also had a negative effect of temperature. And I can't prove this, but I think that that's because in many of our locations, the nectar flow was being shortened by extreme heat conditions. And so we actually found that heat or flying degree days isn't a universal predictor of colony growth rate, because when you have hot weather conditions that might be chopping down the amount of forage you're getting, it's going to interfere. So we did this, and I want to tell you what it did. Well, we then go and do our massive statistical analysis of the entire genome of these 1,000 colonies from around Canada, and we look to say what predicts 2-week weight gain. And without taking weather into account, I found over 9,000 positions in the genome, and that had some influence. And I thought, that's not, it seems like a lot. And then when I took out the effect of weather, when I said how much did they grow after we account for the effect of weather, I found half as many. So what that means is that the weather variability was giving me noise in the data and taking out that effect of weather on growth, letting me see more clearly what the actual genetic markers are contributing to colony growth. So this is a work in progress. It's supported by Genome Canada, Genome Ontario, Genome Quebec, Genome BC. I'd like to thank NOAA and NASA for making their data publicly available, and lots of beekeepers were involved in the project. And I think I might even have time for some questions.
So we have time for 1 or 2 questions. Do I see one? Yes.
Do I go there?
Who has a microphone?
2016 was a very dry year. I'm a Quebec beekeeper, Western Quebec. And you look out at the sun and the temperature, and I was wondering if you looked at the rain, the water, precipitations, both the water that falls and maybe different areas. Like I know a lot of my hives are near wetlands, so when it's really dry, I suppose that, oh, there's lots of flowers by the water. Maybe it's not so bad in my area, but that's just a supposition. So did you look at that kind of water?
Yeah, we did look at that, and the NASA data gives you things like a soil moisture number that should be related to crop's ability to grow. I don't have as clear results for that, but we do have that data. So you're quite right. But my main goal was just to filter out some of this weather variation, not to produce the world's best model of what weather is good for bees.
Is there a second question?